So we'll be solving the boundary value problem given as the squared y, the x squared being the same as negative x, for which x takes some value from 0 to 1, having the boundary values or conditions at y of 0 being 0 and y of 1 being 0. And just before we begin to explore the methods, let us try to solve this problem analytically. And to solve this problem, we'll have to integrate twice. So that is squared y, x squared, being the same as negative x. Now, this will give us the y, integral of the y dx, be the same as negative x squared over 2. But C1, where C1 is the constant of integration. And once we integrate the y dx, then we get y of x being the same as negative x squared plus 1, that will be x cubed over 2 times 3, about 6, plus C1x plus C2. So we have C1 and C2 are the constants of integration. And then the next point would be to apply the boundary conditions. So at x being the same as 0, then we have y of 0 being the same as 0, which is the same as negative 0 cubed over 6 plus C1, which is equal to 0 plus C2. So in this case, we see that C2 is the same as 0. Is this 0 be 0? So C2 is the same as 0. Then at boundary condition y of 1 being 0, that is at x being the same as 1. So we have that negative 1 cubed over 6 plus C1 times 1 plus C2 is already given as 0, as that has been derived. Then we have C2 being the same as 0. Therefore, we now have negative 1 over 6 plus C1. So that C1 is the same as 1 over 6. So, now that we've derived the values of C1 and C2, then we could substitute that into the function so that C2 reduces to 0, and then C1 will be the same as 1 over 6, so that y of x will now be the same as negative x cubed over 6 plus x over 6. And now at boundary condition, for which x is the same as 0, then we'll have y of 0, which will be negative 0 cubed. Once we plug that into this expression, over 6 plus 0 over 6 is equal to 0. And this is consistent with the boundary condition. So this satisfies the boundary condition. Okay, then at x being the same as 0.5, then we have that y of 0.5 will be the same as negative 0.5 cubed over 6 plus 0.5 over 6, which will be the same as 0.0625. So that is the exact solution. At x being the same as 0.5. So we'll take note of this. Now, at x being the same as 1, then y of 1 will be the same as negative 1 cubed over 6 plus 1 over 6, which is the same as negative 1 over 6 plus 1 over 6, which is the same as 0. And once again, this is consistent with the boundary condition. Hence, this also satisfies the boundary condition. So in essence, we can as well conclude that this is the exact solution of the second order differential equation. So the next thing to do is to verify this outcome using some of the known methods. And this time we'll be playing with the use of MATLAB in terms of addressing this problem to see how we are able to use the MATLAB to derive an approximate solution using the finite difference method, the finite element method. We'll also consider the collocation method, the shooting method, and then the Galerkin method, and the finite element method. I think I mentioned that already. So while we play with the use of MATLAB, it is expected that the students attempt to solve these problems analytically in their spare time. So let's share. So now looking at this, in this method, we have applied the finite difference method. And in this case, we have been able to define the interior points to be 10. We could scale down to as little as 2, but the higher the points, the more accurate the approximation will be. And here, we also have taken the value, the internal value, to range from 0 less than x, less than 1. So that is, we are taking on x to take on values from 0 to 1. And if we divide this into n plus 1 equal space of points, then h, which is the step size, will be 1 over n plus 1, such that x sub I is the same as I sub h, for which I takes on values from 0, 1, 2, all to n plus 1. Now that we have gotten the step size, so the implication is that the boundary conditions based on the question given will now be y of naught will be the same as 0, and y of n plus 1 will now be the same as 0. And now that we have to use the finite difference method, we will have to discretize the second order differential equation using the central difference method. And we already emphasized that for the second order differential equation, now the central difference method is given as negative y sub I negative 1 minus 1, negative 2y sub I plus y sub I plus 1 will be the same as h squared, and the same as negative x sub I, which, so for which this is the same as the squared y, the x squared, being the same as negative x, which is the differential equation given. And once we cross multiply this, then we are going to get something like y sub I minus 1 minus 2y sub I plus y sub I plus 1 being the same as negative x, or let us see, let's bring in the h, that will be h squared times, that will be h squared times x sub I. And once we multiply through negative, then that will give us negative y sub I minus 1. That's plus 2y sub I minus y sub I plus 1 will be the same as h squared x sub I. So once we plot the values of I from 1, taking on values for the interior points, okay, and then we'll be able to develop the system of equations. So for instance, if in this case, I is the same as 1, then this equation will reduce to y, that's 1 minus 1, y naught, plus y1 minus y2 will be the same as h squared x1. And we already know from the boundary values or conditions that this is the same as 0. So this equation will reduce to y1 minus y2, which is the same as h squared x1. And we already know what x1 is based on the points that we have, based on the spacing or the time step. So with this, we'll be able to draw up the relationship between the matrix element and the solution that we seek in this update, which will be the same as. And now, okay. Well, that's just a brief summary of what is expected should you attempt the solution analytically. And now, looking this up, we have provided the parameters for which n is the same as 10. So we are considering 10 interior points. So this will be 1 divided by 10 plus 1. That will be 1 divided by 11. So that will give us the number of intervals. That will give us intervals for which between 0 and 1. Then we will define the line space. And then we'll construct the tridiagonal matrix where we have the diagonal and the superdiagonal and all of that. Then we also include the boundary conditions and then display. So let us run this to see if we'll get something close to our exact solution. Now, from the exact solution, we got at 0.5, y 0.5 was the same as 0.0625. Now we have 0.54, blah, blah, so approximately 0.06. So that's it. So these are the points. Being able to evaluate the values. I know 0.9, we're getting close to 0. Okay. And now the same also applies for the shooting method. And when we consider the shooting method, as we explained earlier, we will first have to convert the boundary value problem to an initial value problem. And in this case, we can as well assume that the squared y, the x squared, which is the same as negative s, is the same as y prime prime, then the same as negative x. So for us to do this conversion, if y prime prime is the same as negative x as we have here, then should y prime be the same as v, for instance, then v prime, which should be the same as y prime prime, will be the same as negative x. So now we have two initial value problems to solve. And should we invoke the ODE 45 function from MATLAB, then this could be addressed using the fourth order Runge-Kutta method and the likes. Now, so having converted to the initial value problem, then we describe the functions, then we specify the initial conditions and our initial guess. But the bottom line is, should the initial guess not give us the expected outcome, then we'll have to guess again. But in this case, we'll have to adjust the MATLAB iterative process so as to arrive at an approximate value. So there we go. And then the system of equation is solved. Then we have this. In this case, so let's clear this. So once we run this, once again, we have all of the points at different intervals. For our initial guess. But you observe that since at y1, we did not arrive at 0, this is far from 0. So it means that our initial guess is far from, provided an approximate solution that is far from the exact solution. So we want to now modify our code, and there we have the adjusted code, for which we also converted to the first to the initial value problem. Then we specify the initial conditions with the tolerance value and the maximum iteration with our initial guess. And in this case, we now have to initialize the iteration counter. And then with the while loop, we're able to resolve that and then solved. And then map the error value by calculating the estimated value. And then we adjusted the guess for our boundary conditions. So with this, we'll now run our simulation. So let us clear this. Then we see we got something even better. So we have literally moved from 0.8 to about 0.1. And then we can, literally continue with this adjustment till we are able to arrive at the expected outcome. Now, another interesting method that is considered here is the Galerkin's method. Now, in considering the Galerkin's method, this method actually approximates the solution as a series of basis functions, such that y of x is now the same as sigma I taken on values from 1 to n, c sub I, phi of I of x, where phi of I sub s are chosen basis function that satisfies the boundary conditions. And in this case, using this algorithm, we first have to discretize the domain by dividing the interval from 0 to 1, which is given, into n intervals. And then we'll now choose a test and trial function. Afterwards, we formulate the weak form and then assemble the system of equation and then solve. In the same way, we have n being the same as 2. And just like I mentioned earlier, the higher the time step or point, the more accurate the approximation. And here, we now initialize the global state matrix and the load matrix, for which is derived to be this. And then we apply the boundary conditions to solve this, and then we plot. So let us apply this once again. So LC, then we run. Now, you observe, let's share the entire screen. Now, this is the graph we've got for n equal to 2. Okay? For n equal to 2. What if we increase n equal to 10? Are we going to get a cleaner approximation? So let's go back. Now you will also observe that with the Galerkin's method at time step 0.5, we got exact same solution as we got with the exact solution. Now, if we should modify the time step to say 10, we observe that we have from an approximation that looks something like this. So, something like this. And there, see that this method equally satisfies the boundary values at 0.1 and at 1.0. And the condition 1, and also boundary condition 0. And the next method we'll look at is the finite element method. Now, for the finite element method, we have pretty much the same or something similar to the Galerkin's method, where we have chosen n to be 2, and now the number of nodes to be the same as n plus 1. In this case, it will be 3. And then we define the grid, which should be equally spaced between 0 and 1. And then the time step, h, which is the length of each element. Now here we initialize the global state matrix and the load vector. And then with the for loop, we are able to provide a relationship between the local state matrix for element I and the load vector for element I. And there we have to integrate and then assemble the global matrix. Then at this point, we apply the boundary conditions at y of 0 being the same as 0 and y of 1 being the same as 1. And then we now solve the system of equations. Then we plot the graph and then generate the plots and display the solution. So you see that we actually achieve the same as the exact solution at 0.5. So one more method we'll look up is the collocation method. And we can also see the plot for this, for the finite element method. So that's what we get, where we have the finite element solution and the finite element. So they overlap. Now, for the collocation method. Now, in applying the collocation method, we already know that the squared y, the x squared, is the same as negative x. And we already have the boundary conditions, y of naught being the same as 0, and y of 1 being the same as 0. And to use the collocation method, we first assume the trial solution in the form of a piecewise polynomial. And this polynomial must satisfy the boundary conditions. And here, if we assume the quadratic polynomial, for instance, because it fits with the second order differential equation and boundary conditions, then we can say that y of x is the same as C1 x into bracket 1 minus x plus C2 into bracket C2x squared is a polynomial 1 minus x. Now, having done this, then we can now move on to apply the boundary conditions. So at y of naught at x being the same as 0, then this is the same as 0, since in this case, x into bracket 1 minus x will be the same as 0, because 0 times this process will give us 0. And y of 1 being the same as 0 will also give us 0, since x squared into bracket 1 minus x 0 squared times this is also 0. So now that we have done this, we now have to compute the second derivative of the trial function to match the given equation. And we already know that this is the same as y prime prime being the same as negative x. Okay? Now, if we invoke that such that y prime prime being the same as of x, let's just, it's a function of x, is the same as negative x, then y prime of x will be the same as C1. Okay, so if we integrate, if we differentiate this, the first derivative will be C1 into bracket 1 minus 2x plus C2 into bracket 2x plus 3x squared. And then the second derivative will give us minus 2C1 plus 4C2x minus 6C2x, which will be the same as negative 2C1 minus 2C2x. Now, having done this, we now chose a collocation point within the domain where the residual, that is the error within the trial solution and the differential equation will be 0. And commonly, for the quadratic polynomial, we choose the interval to be the same as 1/2. And if we should do that, then for x being the same as 1/2, that is 0.5. So if we should substitute that into our differential equation, then we now have negative 2C1 minus 2C2 into bracket 0.5 will be the same as minus 0.5. Okay? And then negative 2C1 minus C2 will be the same as negative 0.5. So in this case, we have to multiply through by negative. So we have 2, okay, we have 2C1 plus C2 is the same as 0.5. So we have the first equation. Now, from this, if we, for instance, apply the boundary conditions to the trial equation, say at x being the same as 0, then y of naught will be the same as 0. And this gives 0 being the same as C1 into bracket 0, into bracket 1 minus 0, minus C2 into bracket 0 squared, into bracket 1 minus 0. And this also will give us 0 equal to 0. And this is trivially satisfied. And then when x is also the same as 1, for the boundary condition y of 1 being the same as 0, we also observe that 0 is the same as C1 times 1 into bracket 1 minus 1 plus C2 1 squared into bracket 1 minus 1. And once again, 1 minus 1 is 0 times 0, 1 minus 1 is 0 times 0. Once again, 0 equal to 0, which is equally trivially satisfied. So in essence, the only solution we've got is 2C1 plus C2 equal to 0.5. And here we have two unknowns in this equation or system equation. Now, since the only solution for C1 and C2 is the one from the collocation point 0.5, then we can now solve by making an assumption. So now, in this case, we have 2C1 plus C2 equal to 0.5. So if we assume, for instance, that C1 is the same as 0, okay? Let's assume C1 is the same as 0. Then it means C2 is the same as 0.5. Now, if C2 is the same as 0.5, then, and C1 is the same as 0, then our y of x will now be the same as 0.5 x squared into bracket 1 minus x. Once plugged into the trial equation. And should we apply y of 0.5 at x being the same as 0.5 in this expression, then y of x, or the y of 0.5, will be the same as 0.5 into bracket 0.5 squared into bracket 1 minus 0.5. And this is going to give us 0.0625, which is the same as the exact solution. So there's some level of accuracy using the collocation method. And now, if we should look up what we have here, we now see that we have defined the domain as a equal to 0, b equal to 1, which is the start of the interval and the end of the interval. Then we've defined the number of collocation points to be 2. And then the collocation points interior points where the residual will be 0 have also been specified. Therefore, we define the symbolic variables and then the trial function, which is a polynomial basis function, as described in the analytical example. Then we can initialize. And what do we have? Which is the same as the solution we got.